Hello everyone. In this video, we are going to look at object tracking under occlusion using Kalman filter. And Kalman filter basically combines a model with observations. And for observations, we are going to use both NCC and optical flow, of course, separately. And we want to see what happens. So NCC, normalized cross correlation, we use it for template matching, and we try to directly find the initial template or the initial object in consequent frames. And with optical flow, we measure the displacement between subsequent frames and try to use that as the observations. Okay, so just briefly the theory of it very fast. I have a large video on Kalman filter and I explain everything about it, but just briefly I want to explain a little bit here. Brief theory about it. So when you're trying to find an object in an image, there are two coordinates that you need to find, x and y. And if you use a constant velocity model, then you also need to bring in vx and vy here, which are the velocities of the object in terms of pixels per frame. Okay, so your state vector x of k is going to be basically all of this. Now this x and this x are different. This is a vector x, okay, and if you don't like to call it vector x, call it anything else. This is just the x coordinates in the image. So now the state transition model here is x vector at iteration k plus 1 is a times x of k plus w of k, where w of k is the process noise, and a here is 1, and a is this 4x4 matrix. Now how is that derived like this? I'm gonna explain it. Delta t is the time step between one frame and to the next one, and it's kind of implicit. We don't exactly use that, but if I want to explain it for you, so if I assume that the velocity stays constant, then x at iteration k plus 1 can be as x at iteration k plus the velocity in the x direction, which you call it vx in iteration k, right, times delta t, okay, assuming that delta t is small. And similarly, I can write something for y direction, correct? So these are the first order approximations, assuming that delta t is small. These are approximately correct. And of course, since we assume that the velocities are constant, then the velocity x at iteration k plus 1 is equal to velocity x at iteration k, and a similar thing for the y direction. We assume that they are not changing. So if you write these difference equations in terms of a times x of k, clearly a's are the coefficients of these four entities, right, in these equations. So here, let me show you. The first one is x of k. What's the coefficient of x of k? You see it's 1 for x of k plus 1. Is there any vx of k coefficient? Yes, that's delta t. Is there any coefficient for yk or vyk in this equation? No. So you can write them as 0 times y of k and 0 times vy of k. So if you look at the first row, the number should be 0 delta t, 1 delta t, and 0 and 0. And if you go down, that is exactly what you are going to see here in the first row. Look. Then since your second entity here in this vector is v of x, so you have to go to the equation of v of x. And if you look here in this equation, the only thing on the right hand side is v of x at k, and with the coefficient of 1, nothing else has a coefficient. So there is 0 x of k, 1 vx of k, 0 y of k, 0 vy of k. So you should get a 0 1, 0, 0, and that is exactly what you get. And similarly, the next equation is going to be y, the next one is going to be vy, and so you're going to get these two rows. So basically, as I said, you have to rearrange these equations and basically change the location of the second and the third equation here. Basically this one. Okay, so here I have rearranged it, and if you do that, you can clearly see where A is coming from. And there is no input in this case, because you see in the Kalman filter equations, you always have a B times U of K, correct? So you always have this one as well, but in this case, there is no external input, so that term is 0 here. And as I said, this is the noise that you can consider in these equations. Okay, of course, there is approximations here done, so this is not going to be perfect. There will always some error here. Okay, so if these are the state equations, the state transformation equations, then the prediction stage for Kalman filter is going to be that x hat is going to be the predicted state at the next stage is going to be a times x of k, and the uncertainty associated with this prediction, which we call a state covariance matrix, can be found by its initial value and then pre and post multiplied by a and a transpose. Okay, so this is the uncertainty associated with this prediction, basically, or this one in this case. And so this one is associated with that. And then in the correction stage, where the measurements are coming in, so you have to have a measurement model. Now in this case, the only thing that you are measuring or observing are x and y of the target or the object. So remember that your state has 4 variables, x, vx, y, and vy, and you're only looking at first and third variable. So in this case, your measurement zk, which is this guy, is going to be this H matrix times x, and you can see that this in the first row will pick the first element of x, which is xk, and this in the second row will pick the third element of that, which is yk, okay? So that is your H, and again, clearly there is no extra matrix times U of k because there is no U in this case. And so the only other thing you have is your measurement noise, okay? The uncertainty that you have in your measurement, whether you do it with NCC or any other object tracking method, or you do it with feature matching, or you do it with optical flow, none of them is perfectly accurate. So this V actually is the noise for that. And then in this stage, the corrected value for the state is going to be the predicted one that you got from the prediction stage times the Kalman gain times this term, right? We call it the innovation term, where the K, the Kalman gain, is calculated based on this top formula, P H transpose all the way, right? And R here is, of course, the measurement noise covariance. So R is related to V in this case, right? R is the measurement noise for this V. And your P also gets updated, your uncertainty for the X gets updated through this equation. So these are your 2 update equations during the correction stage, and this is how you find the Kalman gain. Okay, so these are your equations here for a constant velocity model. And we are going to talk about that. But here in what I'll show you, we are going to use a Kalman filter. Why do we use a Kalman filter in the first place? Because if there is occlusion, none of your common object detection methods will work. If you're using a template matching like NCC or feature matching or anything else, when the object goes and hides behind another object, you cannot detect it. So under that case, you easily lose the tracking of the object. And so Kalman filter says during those scenarios that the observations are not available, all I would do is to go through what? Through the prediction. says during those states, all I follow my model. And basically the model will dictate how the object is moving. If the object was moving from right to left in previous frames with some velocity, I assume that, which we call constant velocity in this case, whatever it was, we assume that it is going to keep going in that same direction. It's kind of like the first law of Newton, right? The inertia law, that if the object was going in some direction, unless something happens, we assume it is still going in that direction. That's kind of the same thing here, right? So we keep calculating the position of that in that direction with this last speed that we had, the last time we could do any measurement, and until it shows again. Once it shows again, now probably what I think was the location of it and what I'll see as the location, they are different. Okay, so that's where you see it here. My observation is going to be different than what I think it should be. The difference is called the innovation, multiplied by gain and added to my prediction to do some correction and remove the deviations. Okay, so this is why we use a Kalman filter or any other method that can track objects under occlusion. So here are the two codes that I have written for you. The first one is using Kalman filter with NCC. So your measurement is directly the location of the object where the normalized cross correlation between that region of interest, ROI, in the current frame and the original template is maximum in your current frame. So here is a video in MATLAB which has occlusion in it, and we start at this time where the object can be seen, and then the object goes behind the tree, the person, and then it comes from the other side of the tree. And this is quite a bit a challenging video, and there are several objects moving, but we only focus on one of them. So first we read the frame, and the frames are very small, so each time I multiply them by a size of 3, I resize them so we can see them bigger. Then we use the command IMRect and IMCrop to get me the template. So I manually pick which object, which car, person, whatever, in this case person, is it that I want to track. So I find that template. And then what? Then I'm going to seek that template in all of my subsequent frames with the NCC. Also, as a side, I also have my surf, so I try to track it with the surf features as well. And I have my Kalman filter, okay, and see how each one of them is acting. Now, in MATLAB, if you want to start a Kalman filter, one of the commands that you can use is this command here, configure Kalman filter. So this will start a Kalman filter. You don't need to create all of these equations and write them and do that, although you can if you want. So this will automatically create a Kalman filter for you, an object, and you can ask it to go with a constant velocity model or with a constant acceleration model. Here we go with constant velocity, and I'll tell you why. And then we pick the first two values of the region of interest, because when you do a cropping, it gives you 4 values. Basically the top left corner of the rectangle and the size of the rectangle. So here we pick the top left corner of that as the initial location of the object, because if you look at this configure Kalman filter, this is the syntax for it. So first you have to give it the model. What kind of model is that? You go with constant velocity here, okay? As I said, you also can go with constant acceleration. Then you have to give it the initial location in this case, or initial state values. So in this case, we just need location. We don't need all of the state. We just need the x and y, not vx and vy. So we pick those numbers. Then is there any error that you think initially is in your estimation of the location of the object? So here you see I'm using very small numbers, 100th of the size of the frame. So these are like 10, 12 pixels, something like that in each direction. And then you have to give it a motion noise. This is your model noise, and then your measurement noise. And here I'm going with these numbers. If you don't basically changing these numbers initially will change the initial behavior of your Kalman filter, but over time you will converge, okay, if your model works well. And then I want to show you what is the state transition model for this Kalman filter and what is the measurement model for this Kalman filter. Basically, these matrices that I showed you, A and H, I want to show you those over here. And then you see I go over surf. So I start my surf. First, you have to convert it to RGB to gray. And then for that region of interest, I detect the surf features. I extract the surf features. And then for 40 frames, I keep track of the object. Now, so you see here, I'm getting that frame. I use the predict method of Kalman filter that I made. I use the prediction on it to give me the predicted location. And then later I'll use the correct, which is doing the correction, and I pass to it the Kalman filter as well as basically my measurement here, okay? My measurement. So you see that when you use the correct for Kalman filter, you have to pass to it the Z, the measurement. What does it return if you want? It returns the corrected measurement, the corrected state, and the corrected covariance. So basically it gives you this P, and it gives you this X, and it can even give you the updated Z if you want. These are the things that the corrected correction of Kalman filter returns. In the prediction stage, what it returns is the covariance and the state, and you can see that as well up here, that it gives you X prediction and P prediction. Now the question is, where do I get my measurements, right? Remember, I need to pass it measurement. So here I'm giving it some measurement called corrected location. What is that? That is directly coming from my NCC measurements. So I use my NCC in each frame to locate the best match for my template. You see, I'm passing it the entire new frame and the template, okay? Here I'm giving it channel 1 of the template. The better way to do it is to really apply RGB to gray on the template instead of this, okay? Instead of giving it red channel. And then once I get this cross correlation matrix, I find where the maximum is. And then I find the X and Y of that maximum location. I adjust for the size of the template and find the location, the best location, the maximum NCC. Now, I use this NCC measurement if and only if the maximum NCC I found is bigger than a threshold. Because sometimes NCC still finds something for you, but it's definitely not the right match. Okay, it goes and finds somewhere else, because you should have some minimum C that below which your detections of NCC are basically completely wrong. So here I picked this 0.67, but this is one of the hyperparameters to adjust here. So if my NCC is good enough and it's more than 2/3 out of, because you know maximum of it is 1, if it's more than 67%, I say that, well, it probably found the right template, the correct template, and that location that it found, I'm going to use it as my measurement and pass it to the Kalman filter. Okay? Now, if it cannot pass that minimum, it probably found a wrong template. I'm not going to update. You see, here I'm doing update. In this stage, I say my update in the correction is the same as prediction. So basically here is no updating. Okay, I'm not doing any update. And similarly, you see I'm doing surf. I detect the surf features for the gray frame. And I extract the features and then I try to match them. Now here, look, first thing is I make sure that it detected features in the original template and in the current frame. If it cannot find any in any of them, like it could not find any surf feature for my template in the current frame, I know that using surf is useless because it could not even find one of them. If it did, then I try to match them. And then if the number of match points in the current frame and the original frame is not empty, so it could find at least one or two set of surf points, then I'm going to find the location of the current points and the old points and take their average to call it the displacement of the frame, displacement of the object between original and current frame. And I will add that to what? To my corrected location. And once I have that, then I'm going to call this surf detected location. Otherwise, I'm going to not use this displacement because I could not find any matching points. Now, while I was explaining this, I caught myself with a mistake. That's the best thing you say. They always say if you want to learn something very well, you have to teach it. And that's exactly it. So I found that I was constantly adding the current corrected location with the displacement, but displacement is calculated from my current location from the original one. So this is wrong. Here my reference is original, but here I'm adding that displacement to the current location as opposed to the initial location. So I changed this portion. Instead of corrected location, I made it initial location, and initial location I initially assign it to the first two elements of the region of interest. Okay, so here I modified this part, so when I do NCC, when I do surf detected location, I'm not doing the wrong thing. So here we go. So as a side method, I'm also using surf. See if surf can survive occlusion, which I know it can't. I'm also using NCC as my measurement and observation for the Kalman filter. And I only use it if NCC that I have is more than so much threshold. Otherwise, I don't use it, and I just use my predictions. And at the end, I have to update my region of interest. So I only extract the surf features for that, okay? Because you see that when I basically go about the surf features, right? You see here, when I do surf features, I'm only detecting surf features for the region of interest, not for the entire gray frame. Okay, so I have to update my region of interest based on what I have right now. And then I insert basically shapes and markers around the Kalman filter detected location or corrected location, NCC location, and surf location. And I update my frame with values, and I show the current value that I have, the current maximum C, and animate this for you. So let's go ahead and run this. Also, as I said, I changed this template channel 1 to RGB to gray of templates to compare grayscale with grayscale, not red channel with grayscale. This is more accurate. So let's go ahead and run, see what happens. There we go. So this is the video frame, the video, and here is the guy that goes behind the tree. So let's go ahead and draw some region of interest around him and let the tracking do the job. So the white markers are the surf points. The white window is the surf detection. The blue one is the NCC. And the green one is the FK, the Kalman filter. And you see that here, so far, they were all kind of tracking. Now you see that, look, your NCC is completely off. Your surf lost it because it went behind the object. But look at your Kalman filter, although not perfect, still it is following the object. And when the guy comes out, look what happens. The NCC goes back for a second, although sometimes goes crazy and goes to this location, right? And let me play it one more time because this is really interesting, so we can analyze it together, right? So you see, initially everything is doing a beautiful job. They're all kind of tracking it. NCC finds it alone without any filter. Surf is doing it because it can find some features. And of course the filter, Kalman filter. But now look, this is where he goes behind the tree. You see, NCC goes completely wrong. The features are gone, so the surf stops working. But look, the filter still uses that motion that it had and tries to go. You see, NCC still bad. Sometimes it finds it, but it's not easy. Why? Because NCC is really good for objects that do not change in scale or rotation or their overall shape. This guy, as he moves hands and feet forward and backwards. So your original template is quite a bit different from this one. Still doesn't do a bad job because the object is far away. But if this video was taken from a smaller distance, there is no surprise that sometimes it goes crazy and finds something else. And that's why you need a threshold. Right? Because look here, if I want to say wherever this one is, go ahead and accept it, wherever NCC, accept it as your observation and go ahead and update it. If I do that, this green window right now will be right next to that blue window, because the innovation term is huge here and it is gonna completely makes my Kalman filter corrections be totally wrong. So I put some threshold that if my NCC value is below something, that clearly means I have done something wrong, right? So that is a parameter that you have to choose. And here it shows you the current location of the Kalman filter, the best location that it has, and NCC value and everything. And you see that surf clearly failed after occlusion, NCC failed, but Kalman filter still could kind of track the object. Now, of course, the guy changed his direction. He was going like in this direction along this line, and then he turned and he went this way. But it takes some time for the Kalman filter to go back. If we continue this over several extra frames, and this NCC could come back and detect it, that NCC could bring this green window back around the object, because your observations are getting better and better, and they're gonna basically fix for this deviation. Again, look here. This is the direction that the guy was going, right? And right now, as he turned around behind the tree and moved a little bit to the left, that's what happened to the corrections. So here I added this these arrows for you so you can see better. He was going like in this direction, and that's where the motion model is predicting. But then right after coming out of the tree, you see he's moving in this direction. Of course, he turned around, and so again, it needs some good observations and good measurements by NCC before this green can come back and goes around the object. And you see surf completely stopped. So this is how you do it with NCC. Now, in the second code that I wrote for you, we are doing it with optical flow, not with NCC. So, but we also use NCC and surf again here as separate measurements, okay? And we compare them against the Kalman filter that's the observation of it are coming from optical flow. So the optical flow is done using Farnbach, and I'm using basically 4 levels, scaling of 0.5 and a little bit bigger filter size, because the images are resized by size 3 by factor 3. And so, you know, Farnbach is a dense method, but I'm not going to use all of it. I'm only going to use the portion of it that is inside the region of interest. I again start a Kalman filter with constant velocity, and I will show you the state transition model and the measurement model. By the way, speaking of them, let's go and show you these two that are from the previous code. Look here. This is the state transition matrix, and this is the observation matrix. And if I go back and show you what I had earlier, look, that is exactly this one. That is what we found for observation. That is exactly this one. And if you look at this, it's the same as the one we had, except delta t's are 1 now. So if you change this delta t's to 1, that is exactly what MATLAB has. And why is that this way? Because although we are using these formulas, the problem is when we detect the positions, we don't really care about the time. We go from first frame to the second to third to fourth. So the values that we find, and we call them the current locations, they are really this displacement, this total displacement that we are finding from NCC. If you remember, we had the displacement. These are the thing we find. So if these are the kind of variables that we are using, we can say that we can consider delta t to be 1 between them, because when we go from one frame to the next, again, please pay attention, when I go from one frame to the next, all I care about is the pixel location, and I do not really care about how much time it takes between them, okay? So that is important to consider, because my velocities here in images are not actual pixels per second. They are pixels per frame. So that is the important thing. The thing that I have here, they are pixels per frame and not pixel per time, really. So this should be delta frame, and delta frame for each frame to the next is 1. Okay, so that's why we are only directly using those values and no delta t. It's actually delta f. So now going back to the optical flow. So here we start the Kalman filter, again constant velocity, so that should be the same thing as last time, and we can see the properties of it. And then this is the surf part, that is similar, 40 frames, everything similar to last time. Now this is the only difference. Here I calculate optical flow with estimate flow on the RGB to gray version of the frame. Then what? Then I use the prediction of Kalman filter and I predict it. And then when I want to correct it here, look, when I want to correct it, I should give it some measurements. What are the measurements here? The measurement is what? The measurement should actually be your new location. Now, how do you find new location based on previous one and optical flow? Because optical flow in this case, again, is a displacement. It's not actual velocity. So if I just add the optical flow of the target in the x direction and the y direction, which are displacement x and y, to the predicted location, this should be the new location. And I should pass that directly here as my measurements. Do you see the difference? When we did NCC, we directly got the NCC detections and used it as the measurement. When I use optical flow is displacement. I have to add it to previous location to give me new location, and then this new location is what I pass as my observation. Now here, to make the work better, here I have added a component to kind of change the weight that the Kalman filter puts on the correction part and the portion that it puts on the prediction part. So I'm not using entirely the corrected part. What I'll do is, before I pass to it my measurement, I say my actual current location is a combination of what my prediction of the model says and another basically constant or coefficient times whatever I think it should be based on optical flow. So here I'm doing an alpha blending of my model and my observation. Now you see the gain for model is alpha, the gain for optical flow is 1 minus alpha. Now the bigger the alpha is, the bigger the weight of the model is, and the smaller the weight of the optical flow, and the smaller the alpha is the other way around. So what's good thing about it is when you have occlusion, your optical flow actually does not carry so much good weight because you're calculating optical flow for a template that goes behind the tree. Your model should carry bigger weight. Okay, and the other way around, when your object is moving freely and your optical flow estimates are good, then maybe you have to give bigger weights to optical flow and smaller weight to the model, because your model, you assume the object moves with constant velocity, but maybe he doesn't or she doesn't. He moves with constant acceleration or something. So here you are giving yourself a flexibility, some extra degree of freedom for observation before you give it to the Kalman filter correction. And of course, the rest of the NCC and everything is like last time. I just need to correct the ones I did for the other code. One thing you have to pay attention to is when I give the optical flow X and Y and add it to previous location to get my predicted one here and give it some weight and so on, this flow X and flow Y is not all of this flow that comes from your Farnbach method. It's only the portion of it that is inside the region of interest. So you see here, I'm calculating the X min, X max, Y min, and Y max for the window of region of interest. And then flow Vx and flow Vy, the Vx and Vy component of flow, inside this region, I take their average values to calculate my flow X and flow Y. So for the entire object, I come up with a single number for flow X and a single number for flow Y. Now, of course, when the guy moves and his hands and legs go back and forth, of course, you're not going to get a single number because some parts moving forward, some parts moving backward of his body. So here, this is kind of like the average of the motion of the centroid of the person. Okay, so here you see I'm limiting my optical flow, first of all, to the window around the person and taking an average of it to update the location. Now, of course, that comes with more error for objects that are not rigid and they have parts that are moving forward and backward like a human. Okay, so that causes some error. And then again, plotting everything. So let's go ahead and run this so you see the result of that. There we go. So here we are going to put the template around this person again. And you see in the beginning, again, they are all doing relatively fine. NCC does the job, surf does. Now surf goes away. I only plot the surf if the number of points is more than 0, the number of surf points and the match points. NCC still holding on. Optical flow and Kalman filter still doing, although falling a little bit behind. Why? Because the guy is speeding up. Initially, he was going with constant velocity, but he's speeding up now. And look, NCC failed. NCC clearly cannot detect anymore and catch up with the person. The optical flow still following the person, although kind of falling behind, right? Because as I said, the person kind of speeding up a little bit and maneuvering. Here again is maneuvering. But look here, this is the interesting part. Because the optical flow gives velocity, look, it kind of updated its direction better than last time. Remember last time it was just going in that direction. But here it's kind of turned a little bit, this green window turned a little bit, because as soon as the guy came out, optical flow could, to some extent, find some average velocities for it. Now, of course, you're really going in that region. So it's only good when the person is inside that. Otherwise, you're calculating optical flow on that region, which is not good. Okay, because right now you have no way of knowing where the guy is. Kalman filter think you're here, NCC think you're here, and surf completely failed. So this is the best thing you can get until later something can find this person again. Okay, right? And the bad thing is, because your optical flow here is coming from this window, it might never be able to catch with this guy anymore, okay? Because you're using the wrong optical flow values, and the model is going in this direction because the person was going in that direction. So the bad thing is right now, once it fails, it fails. It's not easy, although a little bit it initially was not bad, but I don't think if you continue this is going to catch up and goes back around that person, but NCC might. Okay, so in general, it's a good idea to use a combination of these two. Now, you might wonder what happens if I use a constant acceleration model. You see, these are the constant velocity model matrices, right? So you might say, what happens if you use a constant acceleration? Because the person kind of speeded up, right? A little bit in the meanwhile, right? So here, I go ahead and uncomment this and comment this one for you. So we go with the constant acceleration, and pay attention. In this case, you're going to have 6 states: x, vx, ax, y, vy, and ay. So make sure that your noise and your process, instead of 2 variables in them, they have 3 variables. Okay, and I'm going to show you right now. You're going to see the matrices. Okay, so let's go ahead and start it around this person again. See what happens if you assume the guy has acceleration. Again, you see initially surf is doing the job, NCC is doing the job, Kalman filter is good. Now here, look what happens to the green filter. The guy is going constant velocity, but the filter assumes that you're going constant acceleration. Look what happens. The filter passes you, overtakes. It goes faster than you because you have not speeded up yet, but the model assumes you have. Look, you see? The Kalman filter completely missed it. And now the NCC misses it, and the surf has lost it long ago, so you lose the whole thing. Okay? So you see that this kind of constant acceleration model could be a little bit dangerous because you assume that your velocity changes. And between one frame to the next, the best thing to do is to go with the constant velocity, not constant acceleration. But here are those matrices, as I said, 6 by 6 and 2 by 6. Okay, so I do not recommend for object tracking to go with constant acceleration in images unless it's a real special case or something. I think it's always better to go with constant velocity. And to me, if you have a method that directly measures the position, not the displacements like optical flow, that could do a better job. Okay, but the problem is those methods, of course, they could be a little bit sensitive to the change in the shape of the object, like NCC. Now, surf is doing a relatively good job until the guy reaches the tree, then surf completely fails. Okay, so instead of NCC, I could have used surf and update the Kalman filter with location of the surf as opposed to the NCC. Here, because the distance to the object is quite a bit large, I am going to use NCC. But you see here, look, NCC could not recover, but surf did. So you could have used surf if you wanted to, because surf could recover after occlusion. NCC is still not. So if you combined surf in the Kalman filter for the observation here, look, where you basically use the correction method here, and for the corrected location, you're directly using what? You're directly using the NCC. You could have come here and did that. So you could have brought this correction here and used this basically surf detected location and passed that to the correction. Hopefully that does a better job. So I'll upload these files for you, give you a download link under video description. Feel free to work with them, give different methods for different observations, see which one of them does a better job. For object under occlusion, you see clearly Kalman filter works with all of them, but some of these observations are much better than the other ones. They have a smaller amount of noise. So it seems like if you use a combination of a feature detector and Kalman filter, that probably can do a relatively better job compared to something like NCC, and then of course compared to optical flow. Okay, So maybe I also write the code for the surf one as well and add it. Then you're going to have three codes. So one is going to be Kalman filter NCC, one is going to be Kalman filter optical flow, and the other one is going to be Kalman filter surf. So you can play with all of them. Hopefully this video was useful to you. I'll see you all in the next lecture. Thank you.